All right. I'm doing part 3 of the value-added attributes. As you can tell, the value-added attributes are a big part of the plus part of NHD Plus, and that's why we're going through this with the 4 sessions on value-added attributes. What I'm going to talk about are some of the tables that are used for divergences and for drainage area. The question about drainage areas and the flow navigator came up before, so I will talk about the table where we have drainage areas. And for some of the value-added attributes related to flow, and then also attributes related to flow line elevations and slopes. Okay, the tables, this is the schematic that Cindy introduced earlier, and these are the tables that I'll be talking about in this presentation. Here's cumulative area, and I'll just talk about these as I go through them. There are several tables in the value-added attributes. Now, here's where you find them. They're, of course, in NHDPlusAttributes, which is the folder for your VPU, and then these are all of the tables that show up in the NHDPlusAttributes folder. Now, I'll talk about the tables that use the divergences other than the value-added attribute table. We have a Frac MP table, and we have a megadiv table. Okay, now in this next slide, I'll go through. These are the 3 types of junctions that we have in NHD Plus. Now, we have our standard convergent junction, which when I was raised in hydrology is what you call a dendritic network, and that's the way I was taught that streams flowed, but by gosh, they don't do that. They diverge a lot. Like Cindy said, we have 60,000 of these puppies in NHD Plus version 2. But we also have, it gets more interesting than that, and interesting as in root canals are interesting. We have complex junctions, and they can get complex indeed. We can have 2 streams coming together, and from that junction, 2 streams coming out. And it can get more fun than that. Okay, Cindy has mentioned about the divergence where the major path, the divergence value is 1, the minor path divergence value is 2. And here's just an illustration of these are in one area. Now, this is generally an area that I would have thought was dendritic, okay? And I just identified all of the flow lines that are involved in divergences in this area that I thought was a nice area. And sure enough, all these red guys here are involved in these divergences that we have in the system. So, indeed, they are all over the place, and you'll, just like me, you'll just have to feel it and let it go. Now, there's a table called megadiv, okay? And megadiv has, defines junctions where there are more than 2 outflows. And this table is really needed for the VAA tables because we needed a way to be able to handle this type of situation where you had multiple outflows from a junction, more than 2 outflows. And so we needed this megadiv table for handling that. This has come up, has been mentioned before. This is called the Frac MP table, and this is where you can override the default values of 0 and 1 for the divergence flow routing. And this is one of the best examples. Actually, this is where the Tennessee River, right near where it flows into the Ohio, And where there's a div Frac MP values, which actually sends 39% of the flow down that path and 61% of the flow down that path flowing into the Ohio River. And it's a really important point in the Ohio and in the junction of the Ohio and the Tennessee. There are a few of these, but you know, they could be really useful for a lot of your work out here in California. It'd be neat to see this table populated more. Okay, now I'm going to talk about some of the drainage area tables. Here's cumulative area, again, which is real nice for the navigator or for you to be able to look at and evaluate how much drainage area is upstream from any given point. And there's also a table called the Headwater Node Area Table, which is very useful. Cumulative area, it has both the total drainage area upstream, and it has what's called the divergence routed drainage area upstream. And the divergence routed drainage area upstream is where you've essentially clipped it off. You've treated the divergences, the minors of divergences. You've treated them like headwaters or like a start reach, and so you're routing everything down the main paths, and then you're not double counting anything. And so the minor paths are treated like headwater start reaches, and it works out very nicely for flow analyses and things like that. It's used a lot, and frankly, I use it a lot also. But we also have the total drainage area for any flow line. Now, the next table, it's called the Headwater Node Area Table, and this is really nice because right here would be the top of a start reach, okay? And this area here, this red area, is the drainage flowing into the top of that start reach. So if you're, for instance, modeling or you're doing an analysis and you want to know what the drainage area is at the top of your start reach, maybe for your most upstream boundary conditions or whatever, the Headwater Node Area Table will give you that value, okay? And this drainage area here is also used in the elevation and slope calculations, which I'll discuss in a little bit. Now, here's the layout of the Headwater Node Area Table. It has our COM ID, and then for each of the headwater reaches, it has the headwater node area in square kilometers given in here, and that's the Headwater Node Area Table. Okay, now I will talk about some tables that affect flow and how you would navigate and route and analyze flow. One of these is the div Frac MP table, and this is a table that I've discussed before, which is earlier in this presentation, which is the way you allocate flows at a divergence where you override the 0 and 1 designations. Down here are two tables, which are the plus flow AR tables, which could be very useful, for instance, in California, for specifying withdrawals of flows from one place and return flows in another place and movement of flows even across basins. We could do flow transfers from the upper Colorado into California even with these tables. So I will talk about the plus flow AR tables now. So it defines flow withdrawals, transfers, and augmentation. Plus flow AR point event, it's an event file, okay, that identifies these points for flow withdrawals or inputs. The plus flow AR itself contains the quantities of flow that are to be withdrawn or added. And here are what the two tables look like together. Here we have essentially 3 events with reach codes and measures, which we talked about before, and what type. We have 2 removals in actually, we're in the northeast right now. If you look at the reach code, it starts 01. That means VPU 01, which is the northeast. And we have 2 removals and 1 addition. And those correspond then over here to, in the plus flow AR table that specifies the quantities of flows. We have a flow removal of 102 CFS, and a flow removal of 186 CFS, and then a flow addition of 186 CFS. So between these two, we're essentially getting a flow transfer, and that's how it's done in NHD+. And this shows how that all those values are. Now I'll show you a map of what is actually happening with these tables. Okay, what we have here is 186 CFS is being removed from this flow line here at this reservoir. 186 CFS is being put in here. In other words, there's a flow transfer taking place there, an implied flow transfer, but that's what's really happening. And somewhere here, someone is pulling out 102 CFS. Not quite sure what for. We don't have that type of metadata on that, but someone is pulling that out. Now, here's what is actually happening in terms of the withdrawal and the addition is this is a pipeline. So actually what we had happening was 186 CFS is actually being transferred due to the pipeline from here over to here. And fortunately, well, Rich Moore and Craig Johnston are from up there, and they know the area very well, and they put this in. They put these values into the table because they knew these were very important flow transfers. And it actually made a big difference in terms of how well our stream flow calculations worked. Okay, now I will talk about elevation and slope. We have a table called elevslope, which has, for each of the flow lines, it has the upstream and downstream elevations, and it has the slope of that flow line. And the Headwater, the node area table actually plays part of a role in the building of the elevslope table. It provides the maximum, minimum elevations and slopes. It's used in our velocity calculations. And what happens is there's sort of a 3-step process. The first is what's called raw elevations are assigned, and then we compute consistent elevations at the nodes, and I'll show how that works. And then we do what's called a smoothing process of the elevations to make sure that we don't have water flowing uphill. Okay, so again, the raw elevations, here, remember I was talking about the Headwater node areas. The raw elevation for the top of this flow line is given as the minimum elevation within this Headwater node catchment. So we get a starting raw elevation at the upstream end there, and we get, for this flow line here, we get a starting upstream elevation because as the minimum elevation here. So now what happens in interior flow lines, the minimum elevation is set to the minimum elevation of that catchment, but the maximum elevation is set to missing for the raw elevations. Then an analysis is done of the network, and at that node, we look at the minimum elevations for the incoming flow lines and get a consistent elevation at that node, which is then transferred to the maximum elevation for this flow line here. So at every node, then we have consistent elevations. So that's the second process that we go through. The third process is an elevation smoothing process, and this is done by level path ID. For instance, in the Ohio Basin, the Ohio River would be done first, and it goes from downstream to upstream, and the elevations are, in effect, what's called smoothed. In other words, it rides along the top of the raw elevations, if you will, so we never have the slopes and the elevations such that the water would be flowing uphill. And actually, this is an example from the Ohio River. So that's how the elevation smoothing works, and it does level path by level path. Now, the slope table, what it comes out with, and this is another table in the attributes, we have a COM ID, the max L of raw and min L of raw. Notice we have a lot of -9998 for the max L of raws because they're the interior values that aren't assigned. And then we get the max L of smooth and the min L of smooth. And then we get a slope for that flow line. And then a slope length. Now the slope length is different from the total length of the flow line in many cases because the slope length is related to the length for the burning. And that's another subject, but a lot of flow lines get trimmed back. And so the elevations that are associated with that flow line are actually related to what gets trimmed back in the elevation processing. So that's the length used to compute those slopes, and those slopes later get used in the velocity calculations. Okay, this is a recap of the tables I've covered in the NHD Plus attributes, and these are all value-added attribute tables that I think several of them will provide you with a lot of important information and hopefully helpful information. And I want to thank you very much. And again, I've covered some of the tables for our divergences, drainage areas, flows, and elevations and slopes. Okay. Let's see, I don't know, do we do questions now?
Can you explain divergence versus total again?
Oh, yeah. Divergence versus total. Okay. When you're accumulating in a divergence routed method, you're moving down the network and you're treating your minor paths as start reaches, and you just leave them as start reaches, and you just keep accumulating that way, and that becomes, for instance, if you were adding up flows or adding up a pollutant, you would just be doing it that way. Whereas with total accumulation, you're taking, when Cindy was showing that picture where when you got a return div, then you recalculated everything. You could be on a minor path, okay, with divergence routing, that's the drainage area for divergence routing might be, 0.1 square kilometer. Whereas total routing might be 100,000 square kilometers because it would be everything upstream. So they're very different, but they serve very different purposes. Think of divergence routing, a lot of times I use that works nicely for flow balance when you're doing a flow model or a pollutant routing model or a pollutant model like the simple model, or in Sparrow, you would want to use a divergence routing so you don't double count.
Yeah, I wanted to just add on total routed flows, especially out in California and in the West, in places where there are a lot of interbasin transfers, you can you can get some total drainage areas that might seem really strange because of maybe a ditch going from one basin to another, including a basin that you don't really think is upstream, but it is actually on a minor path upstream. More questions?
This one back here, Al.
Whoa.
So you said that you calculate withdrawals and inputs into the data, into the flow lines. How do you calculate that? Do you calibrate that using like the USGS gauges, or are those known intakes or withdrawals?
Those are provided by users, okay? That's an input table, and that's a user-created type. It's not something someone may use another model or use another database to calculate those values and put them in that table, but those are just taken as givens. Okay. Also, there's just one of the, that table could actually be used, for instance, you could use it to move water from, like I said, the Colorado into California even. You could move water around vast distances with that table.
So, Tim, does that table only apply to the annual flows or the monthly flows, or are there separate tables?
Well, that's the thing. It's applied to all of them, to mean annual and mean monthly, because it's a cubic feet per second. Now, that would be something I think we would want to look at, would be either a seasonal or monthly values or variable values. But right now, we don't have a time period on that in terms of months or a year.
Tim, you may have explained this already, but my question is for the elevations and the slopes. Do you assign those, for the flow lines, do you assign those same types of calculations for the artificial flow paths in the same way, or is there a difference?
They're done the same way.
Okay.
Yeah, because catchments are built along artificial paths. And what does tend to happen is when you hit an open water body, it tends to just flatten out because of the elevation, because of the NED database itself. And you can see that happening. But it doesn't make a distinction in its calculation process.
Because I have seen what you're talking about, that they do flatten out in those kinds of situations.
It will flatten out when you get into open waters. That's an attribute of the elevation data. Based on some conversations we had earlier this week at AWRA, the elevation does not have the thaw wag going through the open waters. So it just gives us the flat surface.
Thanks.
We're in a